Hello and welcome back to A Slice of Physics. We are now ready to discuss an important conservation law in physics, the law of conservation of momentum. You may think that because this is described as a law, momentum is always conserved, but it turns out that there are certain conditions required to ensure conservation of momentum. And so first we will look at what these conditions are. Next, we will look at an example where we can use this law to determine attributes of motion in interacting objects. In this case, we will look at the velocities after two objects interact in a certain way. In the last couple of videos, we discussed the impulse momentum theorem, where we saw that we could rearrange Newton's second law of motion to get this form: force times time duration equals the change in momentum. I won't repeat those steps, but that was essentially the equation form of impulse momentum theorem. Now, I will put a context to this in just a few minutes in terms of what force and what objects we're talking about, but let's just stay mathematical for now and see what happens in a situation if force is zero. So if the force on an object or a set of objects is zero, then what do we get? Then the left-hand side becomes zero, so we simply get the equation that says the change in momentum has to be zero. And if a change in any quantity is zero, there is no change, which means that quantity is constant. So a consequence of this is that momentum is constant or unchanging. In physics, the word conservation or conserved simply means a value that's not changing or is constant. So the law of conservation of momentum simply states that the momentum of an object or a system of objects is conserved when there is no net force acting on the object or system of objects. It turns out that this very simple looking law is extremely useful in determining forces in collisions, explosions, and other practical situations. So let's take the example of an astronaut who is stranded outside her spacecraft, far away from the Earth and far away from, let's say, even the stars. So here's the astronaut, and you'll have to forgive me, but again, I'm going to use stick figures. I'll just show a big head to say that there's an oxygen mask that the astronaut is wearing, and here she is. And so she is in space and floating outside her spacecraft, which let's say is over here. So there's the spacecraft. I'm not going to show the entire spacecraft, but that's where it is. And the astronaut is here. How does she get back to her spacecraft? Well, in space, there's nothing she can walk on, nothing she can run on, nothing she can push off of. So that becomes a tough predicament. Luckily, our astronaut today has a tool with her. So I'll show that here, that's strapped onto her body. And that tool will become very useful in helping her get back to her spacecraft. All she has to do is take the tool in her hand, throw it away from the spacecraft, which will propel her back toward the spacecraft. And we'll see how that works using conservation of momentum. So as usual, here are our solution steps, or physics recipe, if you want to call it that, for solving conservation of momentum problems. As we saw before, in order to use conservation of momentum, we need the external force or the net external force on an object or system of objects to be zero. That's the condition that ensures conservation of momentum. And in this case, we know that the tool itself cannot be the system because the tool has a force applied on it by the astronaut. The astronaut cannot be the system because the astronaut has a force applied on her by the tool. So we have to choose the system carefully. And it turns out that in this case, if I choose my system as the astronaut plus the tool, there is no net external force acting on it. So a couple of points to cover here before we move forward to solve this problem. So our system that we defined, the astronaut plus the tool, has internal forces. And our condition, we said, was that there should be no external forces. Why is that enough when there are internal forces? Well, Newton's third law comes to the rescue here. Whenever we have forces between objects inside a system, we know that they occur in third law pairs, which are equal in magnitude and opposite in direction. So the force the astronaut applies on the tool is equal in magnitude but opposite in direction to the force that the tool applies on the astronaut. And so the sum of all of those will be zero. So that's why we don't have to worry about internal forces. That really simplifies our approach to this problem where we can ignore a lot of complicated forces acting inside the system. Second, when we define the system as the astronaut plus the tool, the momentum of that system is conserved. But what is momentum of a system of a collection of objects? As you might expect, the momentum of a system of objects is simply the sum of momenta of each of the objects in the system. But we got to be careful about one thing. Momentum is a vector, so when we add the momenta of the individual objects, we got to do that as a vector addition. Okay, so let's get rolling with some of the specifics of this problem here. Let me say that the mass of the astronaut, MA, is 50 kilograms. And let's say the mass of the tool that she's got with her is 2.0 kilograms. And initially, the astronaut is at rest and the tool is at rest. So those are our velocities. And by the way, we already identified the system. In this case, the system was the astronaut plus the tool. And the second step was to sketch the system before and after the event. And in this case, the event is the astronaut throwing the tool. So here's the before picture, before the tool was thrown. Now, once the tool is thrown, we got the picture here where the astronaut is now drifting towards the spacecraft, and we want to find out the speed with which she's going to be moving towards the spacecraft. So the VAF is what we want to determine. This was VAI and this was VTI, the initial velocities of these objects. So the tool by now has been launched, and let's say the tool has been launched with a speed of VTF equals 3.0 meters per second to the right, and this is the unknown we want to determine. What is the speed with which the astronaut will drift towards the spacecraft? Alright, step 2 is done, and for step 3, since we are only dealing with things moving left and right, we can define our coordinate axes as x, that's horizontal, and I really don't need the y-axis, but just for the sake of convention, let me just show y-axis there. So we've already been listing our known and unknown. So here are our known quantities: the mass of the astronaut, the mass of the tool, the initial velocity of the astronaut, the initial velocity of the tool, the final velocity of the tool, and the only unknown is the final velocity of the astronaut. So in order to solve this, since we have defined a system that's got no external force acting on it, we've got its momentum conserved. So we have delta P of the system equals 0, which means that the PI of the system equals PF of the system. Initial momentum equals final momentum when there is no change. Well, what is the initial momentum of the system? As I said before, it's a vector addition of the momenta of the individual objects. So the initial momentum ends up being 50, the mass of the astronaut, times 0, this velocity of the astronaut, plus 2.0, the mass of the tool, times 0, the velocity of the tool. So that's my PIS. And then the PFS is the mass of the tool. Since I know the tool's velocity, I'll start with the tool first. So I've got the mass of the tool of 2.0 times plus 3.0. By writing a specific plus there, I'm recognizing that velocity is a vector, and given our coordinate system, this is a positive velocity moving towards the right. And then I add to that the momentum of the astronaut, which is the mass of the astronaut, 50, times VAF. So there's my equation. The left-hand side of this equation simply turns out to be a big 0. And simplifying on the right-hand side, I've got 6.0 plus 50 VAF. Now it's pretty simple to solve. I got to subtract 6 from both sides, divide both sides by 50, and that'll give me VAF equals minus 6.0 divided by 50, which turns out to be minus 0.12 meters per second. That's the velocity with which the astronaut will drift towards the spacecraft. Since velocity is a vector, given our coordinate system, this negative velocity simply says that the velocity of the astronaut is going to be towards the left, which is a good thing because that's where the spacecraft is. So we have solved this problem, and we have been able to use momentum conservation law to determine velocity with which the astronaut will drift toward to our space station. Now, hopefully, you can appreciate that there are a lot of things going on here with the individual forces applied by the astronaut on the tool and tool back on the astronaut. And when we take bigger systems with more objects, things can get pretty complicated in terms of internal forces. But this momentum conservation law gives us a simple way of approaching a system of objects where, as long as we define the system as having no net external force, we can use the total momentum of the system being conserved to determine unknowns such as velocity in this case or some other unknowns in other cases.